Hello everyone, welcome back to the channel The Learning Tree. Today, let us explore an interesting and familiar science topic, sound. Sound is a part of everyday life. Conversations, music, the ringing of a bell, or the noise of traffic, all of these involve sound. Although sound feels familiar, the science behind it is often unnoticed. This chapter provides an in-depth examination of how sound is produced, the ways it transmits through various media, and the mechanism by which ears receive it. The core concepts involve the study of longitudinal waves, characteristics such as pitch and loudness, the laws of reflection, and the diverse applications of ultrasound. Understanding sound is essential not only for physics, but also for appreciating real-world applications such as energy transfer, medical instruments like stethoscopes, imaging techniques like ultrasonography, and the remarkable ability of animals like bats to navigate using sound. With this introduction, let us now begin the chapter by first understanding how sound is produced. Sound is a form of energy that creates the sensation of hearing when it reaches the ear. Whenever sound is produced, energy is being transferred from a source to the surrounding medium. According to the law of conservation of energy, sound does not appear on its own. Energy must be supplied. For example, when hands are clapped, muscular energy is converted into sound energy. A fundamental principle of sound production is that sound is generated only when objects vibrate. Vibration refers to the rapid to and fro motion of an object about its mean position. This concept of vibration forms the base of the entire chapter and leads naturally to observing different ways in which vibrations are produced. Sound can be produced through various actions, such as plucking, scratching, rubbing, blowing, or shaking objects. In the human body, sound is produced when vocal cords vibrate as air passes through them. A stretched rubber band produces sound when plucked because it vibrates rapidly. Even small creatures like bees generate a buzzing sound due to the vibration caused by their rapid movements. A few simple experiments with a tuning fork clearly show the presence of vibration. When a tuning fork is struck against a rubber pad, it starts vibrating. Touching the vibrating tuning fork to a suspended ball causes the ball to move, showing that vibrations transfer energy. When the tuning fork is placed on a water surface, ripples form, proving that sound-producing vibrations create physical disturbances. These examples firmly establish that vibration is the source of all sound. Let us now move on to understand how sound travels from one place to another. Sound does not travel in empty space. The substance through which sound moves is called a medium. A medium can be a solid, a liquid, or a gas. Sound travels from the point where it is produced to the listener through this medium. A crucial idea must be understood clearly. The particles of the medium do not travel from the source to the ear. Instead, only the disturbance or vibration moves forward through the medium. To understand this process clearly, the mechanism of sound travel must be examined step by step. When an object vibrates, it pushes or pulls the particles of the surrounding medium from their normal positions. The displaced particle then exerts a force on the neighboring particle, causing it to move. After transferring energy, the first particle returns to its original position. This process continues from particle to particle, forming a chain of energy transfer. In this way, the disturbance moves forward through the medium without permanent movement of particles. Eventually, this moving disturbance reaches the ear and produces the sensation of sound. This systematic movement of disturbance introduces the concept of waves. A wave is defined as a disturbance that travels through a medium by setting particles into motion. Since sound travels by causing particles of a medium to vibrate, it is classified as a mechanical wave. Mechanical waves require a medium and cannot propagate through a vacuum. Air is the most common medium for sound propagation in everyday life. Understanding sound as a wave helps explain its behavior, structure, and properties. When a vibrating object moves forward, it pushes air particles closer together, creating a region of high pressure and high density called compression. When the object moves backward, particles spread apart, forming a region of low pressure and low density known as rarefaction. As vibration continues, alternating compressions and rarefactions are produced, forming a sound wave. Pressure and density are directly related. More particles in a region result in higher pressure, while fewer particles result in lower pressure. These repeating patterns define the structure of sound waves and lead to their classification. A longitudinal wave is a wave in which particles of the medium move parallel to the direction of wave propagation. Sound waves are longitudinal because particles oscillate back and forth around their original positions rather than moving forward permanently. A simple activity using a slinky demonstrates this concept effectively. When the slinky is pushed and pulled, regions where coils are close together represent compressions, while regions where they are farther apart represent rarefactions. This activity clearly shows the longitudinal nature of sound waves. To contrast this, another type of wave must be understood: transverse waves. In a transverse wave, particles oscillate up and down about their mean position, perpendicular to the direction of wave travel. A common example is water ripples formed when a pebble is dropped into a pond. Light is also a transverse wave. However, unlike sound, light is not a mechanical wave because it does not require a medium and does not involve particle vibrations or pressure changes. With these distinctions clear, let us turn our attention to the measurable properties of sound waves. Sound waves are described using three main characteristics: frequency, amplitude, and speed. Another important term is wavelength, denoted by the symbol lambda. Wavelength is the distance between two consecutive compressions or two consecutive rarefactions. The SI unit of wavelength is the meter. These characteristics help quantify and compare different sounds. To visualize these properties, graphical representation is useful. Sound waves can be represented graphically as variations in density or pressure. The crest of the graph corresponds to a region of maximum compression where density and pressure are highest. The trough represents a region of maximum rarefaction where density and pressure are lowest. This representation helps link physical particle motion with wave diagrams commonly used in physics. With this visualization, the other two characteristics of sound, frequency and time period, can now be understood easily. Frequency, represented by the symbol nu, is the number of complete oscillations occurring in 1 second. Its SI unit is Hertz, named after Heinrich Rudolf Hertz. The time period, represented by T, is the time taken for one complete oscillation. The SI unit of time period is the second. Frequency and time period are closely related by the formula. Nu is equal to 1 by T. This relationship shows that higher frequency corresponds to shorter time periods. This concept directly influences how sound is perceived. Pitch refers to how the brain interprets the frequency of a sound. Faster vibrations produce higher frequencies and are perceived as higher pitch sounds. Objects of different sizes and conditions vibrate at different frequencies, producing different pitches. A high-pitched sound has more compressions and rarefactions passing a point in 1 second than a low-pitched sound. While pitch depends on frequency, another important perception, loudness, depends on amplitude. Amplitude is the maximum displacement of particles on either side of their mean position. The loudness or softness of a sound depends on its amplitude. Amplitude increases when greater force is used to produce vibration, such as striking a surface harder. Sounds with larger amplitude carry more energy and can travel greater distances. Thus, louder sounds are associated with higher energy levels. However, loudness and intensity are not exactly the same. Intensity is defined as the amount of sound energy passing through a unit area per second. Although intensity and loudness are often used interchangeably, loudness depends on the physiological response of the ear. Two sounds with the same intensity may be perceived as having different loudness if the ear is more sensitive to one frequency than the other. This distinction highlights the difference between physical measurement and human perception. There is another characteristic which will help distinguish sounds further: timbre. Quality, also called timbre, allows distinction between sounds of the same pitch and loudness. A tone is a sound with a single frequency. A musical note consists of a mixture of several frequencies and is usually pleasant to hear. Music has rich quality, while noise is unpleasant to the ear. Timbre explains why the same note sounds different when played on different instruments. Now that we have got acquainted with the different characteristics of sound, let us now pay attention to how fast sound travels. Speed refers to the distance a compression or rarefaction travels in 1 second. The speed of sound is given by the formula V is equal to lambda nu. Under the same conditions, speed remains nearly the same for all frequencies in a given medium. Sound travels much slower than light, which explains why lightning is seen before thunder is heard. Speed also depends strongly on the medium itself. The speed of sound depends on the properties and temperature of the medium. As temperature increases, the speed of sound in air increases. At 0 degrees Celsius, the speed of sound in air is 331 meters per second, while at 22 degrees Celsius, it increases to 344 meters per second. Sound generally travels fastest in solids, slower in liquids, and slowest in gases. At 25 degrees Celsius, sound travels at 6,420 meters per second in aluminium, 1,531 meters per second in seawater, and 346 meters per second in air. These differences explain many natural and technological phenomena. Reflection of sound is another important behavior. Sound reflects from solid or liquid surfaces in a manner similar to a rubber ball bouncing off a wall. The laws of reflection apply to sound just as they do to light. The angle of incidence equals the angle of reflection when measured from the normal. The incident sound, reflected sound, and the normal all lie in the same plane. Reflection requires a sufficiently large obstacle, which may be smooth or rough. This reflection leads to phenomena like echo. An echo is the reflected sound heard separately from the original sound. the sensation of sound persists in the human brain for about 0.1 seconds. To hear a distinct echo, the reflected sound must reach the ear at least 0.1 seconds after the original sound. At 22 degrees Celsius, the minimum distance of the reflecting surface must be about 17.2 meters. Multiple reflections cause the rolling sound of thunder. Reflection also leads to another effect called reverberation. Reverberation is the persistence of sound in an enclosed space due to repeated reflections. Excessive reverberation causes sounds to overlap, making them unclear. To reduce reverberation, walls and ceilings are covered with sound-absorbing materials such as compressed fiberboard, rough plaster, or draperies. Seats in halls are also designed to absorb sound. Controlled reflection is useful in many applications. Megaphones and horns use multiple reflections to direct sound waves forward toward listeners. In a stethoscope, sound from the heart reaches the ears through repeated reflections inside the tube. Concert halls are designed with curved ceilings to distribute sound evenly. Soundboards placed behind stages help spread sound across the entire hall. These applications show the practical importance of sound reflection. Next, let us explore the hearing range of sound. The audible range for humans extends from approximately 20 Hz to 20,000 Hz. Children under 5 years of age and some animals can hear frequencies up to 25 kHz. As humans grow older, sensitivity to higher frequencies decreases. Sounds outside the human range also play important roles in nature. Sounds below 20 Hz frequency are called infrasound. Animals like whales, elephants, and rhinoceroses produce infrasound as low as 5 Hz. Earthquakes generate infrasonic waves before the main shock. Sounds with frequency above 20 kHz are called ultrasound. Animals such as bats, dolphins, porpoises, and rats produce ultrasonic sounds. Moths have developed sensitive hearing to detect bat squeaks. Ultrasound is widely used in technology and medicine. Understanding the properties and characteristics of sound helps in designing hearing aids. A hearing aid is an electronic, battery-operated device designed for people with hearing loss. The microphone receives sound waves and converts them into electrical signals. The amplifier increases the strength of these signals. The speaker converts the amplified signals back into sound and delivers them to the ear. This device helps improve hearing by increasing sound intensity. Sound can clean objects. Ultrasound is used for cleaning objects with complex shapes such as spiral tubes and electronic components. High-frequency vibrations detach dust and grease from surfaces in a cleaning solution. Ultrasound is also used to detect cracks and holes in metal blocks used in large structures. Ultrasonic waves reflect from defects, while ordinary sound waves bend around them. This makes ultrasound highly effective for quality testing. Medical applications are equally important. Echocardiography uses reflected ultrasound waves to create images of the heart. Ultrasonography is used to examine internal organs such as the liver, kidneys, and uterus. It helps detect stones, tumors, and other abnormalities. Ultrasound is widely used to monitor the fetus during pregnancy. Kidney stones can be broken into fine particles using ultrasound, allowing them to be flushed out through urine. These applications show how sound benefits healthcare. Sound is a longitudinal mechanical wave produced by vibrations in a medium. It travels through compressions and rarefactions, transferring energy without permanent particle movement. Key properties of sound include wavelength, frequency, amplitude, and speed, with speed given by V is equal to lambda nu. Sound follows the laws of reflection, producing echoes and reverberation. The human audible range lies between 20 Hz and 20 kHz, while infrasound and ultrasound have significant natural and technological applications. With this summary, we have come to the end of this chapter. If this video helped you understand the lesson better, please subscribe and share the channel link with your classmates on WhatsApp and other social media platforms. Thank you for listening. See you in the next video.